Hello. You should see my desktop. You should be able to hear me. Does everything seem okay?
Yes.
Okay. What's that about? Okay. Uh, let me get things ready. So first, remind you that there is a homework assignment due today. There'll be another one up there within a day or two with what we're with more ML programming. Okay. If you have questions about this homework assignment, please come to office hours. Send me emails. Ask me questions about them. Yeah, I'll try to answer all the questions. I got a little bit of a backlog of questions right now, so some of you may have sent me emails and not got an answer yet. I've got a little bit of a backlog, but I'll try to answer everything. But if you have questions about the homework assignment, well, first off, does anybody have any question like right now? Is there anything about this homework assignment anybody wants to ask about right away? Any question about the homework assignment? Anybody have a question about the homework assignment? This one here. Anything? Okay. Okay. If there's no question, you know, send me an email if you have questions or come to office hours. Okay. And then what we're going to do today is now remember that homework assignment is all about recursive functions. Everything in this one is about writing recursive functions. Okay. Um, the the next homework assignment is going to be about what we're talking about, the next chapter of the book, which is the uh, the next chapter, which is this third look of ML. It's got a couple topics in it. The the main topic is these higher order functions, and that's what the next homework assignment is going to be about. Is higher order functions. Okay. So what we talked about the other day was this stuff about function values and anonymous functions. We're going to finish that today. Say something about what they mean by more pattern matching. This is just an aside. It's got nothing to do with it's really got nothing to do with the rest of the chapter. So it's an interesting little piece of ML that he stuck into this chapter, but it's not relevant to the rest of the chapter. Function values and anonymous functions is very relevant to higher order functions. That's the main topic of the chapter. But you need this as a nice little prerequisite to understanding higher order functions. And then currying is another interesting idea related to higher order functions. And then he talks about some of the predefined higher order functions that comes with ML. So the real topic of the chapter is higher order functions, and that's what the next homework assignment is going to be about, higher order functions. Okay. Now, let me close that. Now, what we talked about the other day was these idea of function values and anonymous functions. So we looked at these examples. Let's just review it real quick. You know, the idea. Let's see. Um, the idea is kind of like what really is a function in mathematics, and the key thing is a formula like that's not a function. We call that an expression. Okay, that's not a function because you have to tell me which one of these is the input of the function. The function is something that takes an input and gives you back an answer. And here, you know, it might be that all of these are inputs to the function, but usually when you see mx plus b, only the x is the input to the function. And the m and the b are constants. So you think of them as constants. Now, from the programming point of view, like here we see in Java, from the programming point of view, m would be some constant that's defined somewhere else in the program, and b is a constant defined somewhere else in the program, and x is the variable of the function. Okay. Now, in Java, you can only define functions this way by giving them a name. Okay. And that's essentially the math formula like this. Well, here, actually, down here, I changed it so that all the variables in this formula are part of the function. So this is a different function than this one is. It needs 3 numbers to give you back an answer, whereas this function only needs 1 number to give you back an answer, but it uses these constants. Okay. So it needs 3 things, but 2 of them are constants, and then 1 of them is the input to the function. Here, all 3 things are inputs to the function. So when you define this function in Java, you have 3 parameters. Okay. Now again, the function's been given a name here, and it's been given a name here. The thing in ML is that we want to be able to, in ML, we want to separate naming the function from defining the function. We want anonymous functions. Okay. Now we didn't get that far. Now that's starting down here when you say, well, this is what we mean by a function that has the input x and the rule x times y plus z, where y and z are constants that somebody defines for you. This is our way of defining a rule of a function without saying what the name of it is. So that's the anonymous function that the book is talking about. It describes a function without having to give it a name. Okay. Now, here's another way to think about that. Let me open a document and just type some more some notes. Okay. Here's a real dumb idea. There's 5. That's a number. Okay. In a sense, you can call that an anonymous number. I didn't give it a name, though. It does have a name. You think of it as the name is 5, but in a sense, you could also think of it as it's anonymous because I didn't give it a name in my program. See, there the number's got a name. It's got a variable for it. Okay, so you can think of this as an anonymous number, but nobody ever calls it that. But what people do call it is a number literal. That's referred to as a number literal. Okay, another example of a number literal would be you can write a number in hex. Okay, you can write a number in hex. That's there's a number. Here's a number. That's a number. Yeah, and you can store that in an int in Java. It's an anonymous number because I haven't given it a name yet, and it's a number literal in hexadecimal. Okay, people, you use them sometimes when you're programming. You write your numbers literals in hexadecimal. Okay, so a number literal means a specific number, and then if I want, I can give it a name. Okay, so I can name it, and if I want, I can figure out what it means in decimal. I don't know if Google will tell me what that is offhand in decimal. Google's a calculator. I can't remember if their calculator is that smart. Okay, 2,748. Okay, so Google looked it up. So that number is a literal. It's a way of writing the number 2,748. It's a different literal than that one. That's a number literal, and that's a number literal. And they both represent the same number. Okay, all right. So here's an idea: number literals and anonymous numbers. But here I give the anonymous number a name. Now, here's a weirder idea. There's a function literal or an anonymous function. So there's a anonymous function, but actually a better name for it is a function literal. It's literally a function. Yeah, it says my function is takes in a number, squares it, and adds 4. That's what my function is. So we sometimes refer to these as function literals. I think that's actually even a better name than anonymous function. Okay, because you don't ever call that an anonymous number. Nobody's ever going to call 5 an anonymous number, but they'll often say it's a number literal, because here's another literal for that same number. Okay, this is a number literal. There's a number literal that's given a name. There's a number literal. It's anonymous. It doesn't have a name yet. Here I gave it a name, so I can make that more Java-like. I've given the anonymous number a name, but a better way to think of it is I give y the value of that number literal. This is a function literal. That's what you should think of it as. Okay, that's a function literal. And in ML, you write fn in front of that to make it work. Okay, in ML, you write fn, then you write the function literal. In some languages, you don't need the fn in front. In some languages, that's enough to be a function literal. ML wants you to put the fn in front. Okay. Now, just like I can take that number literal and give it a name, I can take this function literal and give it a name. So, for example, G, if I wrote it in ML, I'd say val G. That's how I declare a variable. G is a name for the function fn of x goes to x squared plus 4. Okay. I gave the function literal a name. That's why I don't like the phrase anonymous functions. Kind of yeah. Here, what I'm doing is I'm giving the anonymous function a name. But then it's not an anonymous function if it's got a name. That's why anonymous function, it confuses a lot of people, because in a way it doesn't make sense. You write code like this and you say, oh, I have an anonymous function G. Well, it doesn't make sense to have an anonymous function G, because G is the name of the function. Okay. Oh, this is shorthand for writing this in ML. Fun G of x equals x squared plus 4. These are synonyms for each other, except that this lets you say that's the function literal. There's the name for it. This just kind of blends it all together like math does. It just says I have a function G which takes in an x and it does this. Okay, so I don't have a separate notion of the name and the function literal. That's not a function literal there. That by itself is not a function literal. If I write it this way using the and you don't use, if you write fun here, it won't work. Okay, yeah, you don't write fun here and then use the fn notation here for function literal. So if you're going to use the fn notation, you would write val here for a variable. I have a variable G whose value is that function literal. Just like over here, I could say I have a variable Y whose value is the hexadecimal literal ABC. I don't know if ML has hexadecimal literals. We can try. I don't know if ML, well, we can actually. No, ML doesn't seem to have hexadecimal literals. Okay. Did I do that right? Oh no, I typed that wrong. It's 0x. No, it does have fun. Yes, yeah. It's 0x, not yeah. See, it's 0x, not OX. I typed it wrong a minute ago. Okay. 0x, that's kind of standard across most programming languages. You use 0x to say that something is a hexadecimal literal. So here ML did the conversion for me. I wrote the literal number 0x ABC, and ML just translated into the integer literal 2,748. Okay. All right. Now, in a sense, nobody would say I gave a name to that anonymous number, but people would say I gave that number literal to the Y holds that literal value. Okay. Now down here, what I'm doing is saying there's a function literal, and here I gave that literal a name. So that makes more sense. Giving the function literal a name makes more sense than giving the anonymous function a name. Giving the anonymous function a name kind of just confuses things. So I think a better way to say is giving the function literal a name. Okay. Just like, so function literals represent these things that are functions, just like this represents a thing that's a integer. Okay. Java doesn't make as much use of function literals as ML does. In fact, Java didn't even have function literals until a few years ago. Java now does have these function literals, and they're really nice to have in the language. And you don't write them this way. I think in Java you write them just like that. Okay. There's a whole bunch of different ways that function literals are written. So for example, in ML, it would be fn x, that arrow, x squared plus 4. In some languages, you would just write x arrow x squared plus 4. Some languages, they change the arrow a little bit, and they use an arrow that looks like that. In JavaScript, you write out the word function, X. Oh, I can't remember if you write equals. I think you write it with an equal sign in JavaScript. I think in JavaScript, you write the function literal that way, I think. Okay. In C++, if I remember right, you write it this way. You put a pair of square brackets in front of the X and then an arrow like this, I think. I remember the function literals in C++ start with a square with square brackets. I can't remember if they use an arrow here. Let me see real quick. Look up C++ function literal. So you notice that Stack Overflow calls them anonymous functions. People like to call them anonymous functions. Another name for them is lambda expressions. Okay, so over here, let me just point out that the words we use, here's a whole bunch of words. Anonymous function, function literal, function value, because this is the value 5, right? That's the value 5. That's the value 0xabc. So you can think of this as a function value that you store in the variable g. So many people call them function values. They're also called lambda expressions for historical reasons. They're called lambda expressions. And some people call them closures, but that's not a very good name for them. But if you Google this stuff, you'll see a lot of people refer to them as closures. This is probably the most common word to refer to this idea. People like to refer to them as anonymous function, but it's kind of confusing because that doesn't look very anonymous. That doesn't look very anonymous. It's called G. This part is the anonymous function. And then here, this gives the anonymous function a name, which to me is kind of messed up to talk about giving a name to anonymous function. It's not anonymous anymore. I think a better thing is literal, because that's what we use for numbers. We refer to them as function literals. So if I ask how to do a C++ function literal, I notice that the stack. I got a different answer here. Here it refers to anonymous function. Here it refers to lambdas. Okay. See what happens if I get function literal. User defined they're literal. Okay. Let's look for an example. Oh, this is all literals in C++. Number literal. Oh, I got a page for all. I didn't get function literals. I got all the possible literals. I don't even know if function literals will be in here. Most of them are going to be number literals, Boolean literals, string literals. See, here's all the floating point literals. They probably don't even have the function literals on this page because they're kind of new. See, oh, no, you use square bracket, you use braces. You put the body of the literal inside braces. And notice the examples are, the notation is kind of a mess. Well, here they show an arrow. Maybe there's more than one notation. The C++ notation is kind of, I remember it's very messy. Their notation for function literals is not easy to work with. Okay. And then I could ask for Java function literals. Oh, notice it. What is the difference between function literal and values? The answer is there isn't any difference. Function literal is just another word for function values. which are also sometimes called lambdas. Okay, so let's see, look for an example of one here. They're used in Java and C++ a little bit, not as much as ML. And one reason is because the notation is just a big mess. Java and ML just can't get the notation quite right. Okay, there's a function literal. This one has no inputs, and it uses this arrow here. So in Java, it would look like this: x goes to x squared plus 4. Okay, so there's all these different notations. There's a whole bunch of different languages. They've come up with different ways of describing the idea of what's the input and what do you do to compute it. And if you want, all of these can use some other variable. Like that would make y, since it's not one of the inputs, that makes y something that has to be defined elsewhere in the program. And all of these would allow you to do that. All these languages allow you to say, my function literal uses some variable that's not one of the inputs. Okay, and when you do that, that variable has to be defined somewhere else in the program. Okay, so anonymous function, function literals, function values, lambda expression, and closure are all taken as synonyms for each other, as a way of saying describe a function without naming it, and then you can give it a name as a separate step like this. You can supply a name for it, just like you can supply a name for that number value. You can give it a name. You can take that number value and give it a name. You can take that function literal and give it a name. Okay, so that's the first important idea that's in this chapter that we're working on, is the idea that you can separate the naming of a function from describing a function. And the question is like, why do you want to do this? What's wrong with the regular way of defining functions in ML, like that? Okay, remember, this is just a shorthand for this. So what's the need for this shorthand? It's shorter to write than this is. So why do you want this notation here? Okay, so we're going to see why when we talk about the higher order functions. We'll see some uses of anonymous functions or function values, function literals. We'll see some examples of when it'd be nice to use them. Okay, all right, so that's the first thing, is this idea that we can separate the idea of a function from the name of a function, and that we'll see that that's a useful thing to do, as opposed to, like all the examples we did, all these other examples here. In traditional Java notation, you can't separate the name. See, the name's buried. See how in all that boilerplate, there's the return type, there's the input parameters. Notice how the name is stuck in the middle of that. You can't somehow pull the name out and say F is this thing. See, the name part of it is buried deep inside of the whole definition. Same with C++ and C and all that. So these languages, with this notation, the traditional notation, the name is buried very much in the definition. Now that's work that, for years and years, that was plenty fine. It took a long time for people to think of a good reason why they'd want to separate the name from the rest of the function. And the ML people were, again, part of the people who pioneered this idea that it's worthwhile thinking of separating these, of having the function exist on its own as a function value, and then you could give a name to it as a separate step. Okay. All right. Now, that's the function value anonymous function idea here. Okay. Let's go back to this one here. This he calls it more pattern matching. Let me show you what he mean, how I think of what he means. Okay. You see, I got an example here. I'm going to open it in the text editor and then run it in ML. This is an ML program. Okay. I'm going to define a function 1, 2, 3, 4, 5 different ways. Okay. Two of these ways you've seen already, and then there's three new ways of defining the function. Okay, so it's a kind of a silly function. If you give it x, you get back 0. If you give it 1, you get back the string 1. If you give it 2, you get back the string 2. If you give it any other number, it just two strings it. So if you give it a number 17, you get back the string, quote, 17, quote. Okay, so silly little function. Here, it's written without pattern matching. So it's written function f1 of x. If x is 0, then return that. Else, if x is 1, there's no pattern matching going on here. Okay, here's the way we've been writing our programs using pattern matching. So now this is called clauses. We didn't use that term, but now it's worth pointing out that when you write functions this way using pattern matching, each pattern is in a clause. So this is sometimes referred to as clausal function definitions, or function definitions using clause. So f on the pattern 0, which only matches the 0 literal, gives you 0. F2 on the pattern 1 returns 1. F2 on the pattern 2 returns 2. Now this pattern would match any input that isn't 0, 1, or 2. So that, now notice if I switch the order of these patterns, like if I took this pattern and put it at the front, the function wouldn't work anymore. Here the order, the if statements didn't matter, other than the fact that this is the else clause. Okay, in a sense, that's what this is acting like. This is like an else clause, because if it didn't match this pattern, it didn't match this pattern, it didn't match this pattern will match everything else. Okay, so in a sense, it's acting like an else clause, but it's not an else clause. There is no such thing as a else pattern. This is anything that doesn't work here falls into this thing here. Okay, that's not how this works. It's just that this pattern will match anything. Okay, so if I moved it up farther, like if I were to do something like this, the function won't work right. Okay, because now 0 will match that, 1 will match that, x will match everything else, and you'll never get to that pattern there. You'd never get to that pattern. Okay, so this is clausal functions. Okay, you're saying the function is named f2, and then you give it pattern, value, or that pattern. You read these as ors. You read these as essentially or. So f on 0, or f on 1, or f on 2, or f on any, a pattern that matches anything else. Okay, now here's a way of defining the function that now I'm using a function literal on the right-hand side. And this is how you write clauses for function literals, except they're not called clauses anymore. Now they're called rules, and they have a slightly different notation. And this is confusing because this, and this look almost alike, but they're not. Notice that there's a subtle difference. Here I'm saying fun with the name of the function, and the pattern follows the name of the function. And I have to repeat the name of the function and then the pattern. Repeat the name of the function, then the pattern, with the bar in front. Here I say function literal, so it's anonymous. There is no name for it. So the function value is, and then I write a pattern, but it's called a rule now. And then I say what the result is for that pattern. But notice I use an arrow like an anonymous function. Okay, it's sort of written kind of in the form of anonymous function, but it's written with multiple patterns. So this is saying function on this pattern gives me that answer. On this pattern, it gives me that answer. On this pattern, it gives me that answer. And on this pattern, which now will match anything that's left, it gives me this answer. Okay, so this is writing an anonymous function with rules, or a function literal with rules instead of clauses. Slightly different notation. They mean exactly the same thing, but they're just two slightly different ways of writing it. Some people don't like this notation because you have to keep repeating the name of the function. Like if I decide to call that function Bob, now I got to change Bob to Bob and Bob and Bob. Okay, it's annoying. Some people think that's actually kind of an annoying feature of this style of programming. So some people don't like it. On your hand down here, if I want to call this function Bob, there it is. He's called Bob now because the name only shows up in one place. So some people think that this is a superior style, that using rules on a function literal is superior to using clauses on a function definition. Okay, it's 6 of one, half dozen of the other. Some people like one way, some people like it the other way. But the notations are kind of, they're just different enough that it can be confusing. Like, I wrote this up mostly for myself as a little dictionary to keep straight all the different notations. I like this example because I use it, I go back to it to remind myself how to write this style of function versus this style of function, because it's just enough to give you a sense of like what to do to change the styles. You know, very similar. This one uses equals, this one uses the arrow, this one has the name just one time. Okay, so there's clauses, there's rules. Now here's what the book wanted to bring up. There's instead of putting the patterns in the function literal or the patterns in the function definition, you can put the patterns in what's called a case statement. Okay, so you could use case statements anywhere you want in ML, but case statements are another place where you use patterns. Okay, well, actually, in this case, they use root patterns in rules. Okay, so here I'm saying that, notice I'm back to the function notation. So I'm back to using a function f4 of x is, now I do a case on x. This is kind of like a glorified case statement in Java or C++, though it's a case statement using pattern matching. Okay, so I say case of that pattern or that. Notice that there's no vertical bar on this one. Okay, see the notations are, that's why I have this little dictionary to help me keep straight all these different notations. When you use the case statement, there's no vertical bar on the first pattern. But when you use the fun notation or the FN notation or the fun notation, well, actually here, even there's no bar on the first pattern here either. So usually we indent this pattern down below. So if I could actually make this one look like the others, but it wouldn't. If I did this and then put these over here. So that would make it kind of look more like the others. Okay, case X of, but usually people don't write it like this because it starts pushing things off too far on the screen. Okay, so there isn't a bar on the first pattern, just like here, but usually people write the first pattern on the line just below the case of for readability purposes. So this is the style that people use. Case X of, first pattern, second pattern, next pattern. Okay. Notice that I could write a wildcard here. Why couldn't I write a wildcard there? That won't compile. And I cannot write a wildcard there. That won't compile, but I can here. Why? Analyze the code. Look at the code carefully. Pick it apart. Read every letter in the code. Why is the wildcard okay in this one, but not in the others?
Because you're using X.
What do you mean I'm using X? I'm using X here.
Into string.
What?
If you just do the underscore, you don't use, it doesn't keep X for the into string.
I'm not sure what you mean. Okay, you have to, yeah, like, yeah, I think you're on the right track, but you have to explain it a little bit better. What's wrong with that underscore?
Doesn't it just disregard the X or whatever
What
the input
X?
is?
There's X.
The input?
Input, right. It disregards the input, right? It never gives it a name. Okay, so what's wrong with this X?
It has nothing to reference.
Right, it's never been declared. See, let's use programming terminology. Let's talk as programmers. This X has never been declared. When I do this, that declares X. X is the thing that matches the input. See, X is the input parameter now. X matches the input, so I'm repeating whatever the input was here. If I use an underscore here, I'm saying match the input, but don't declare any variable. So this X is undeclared. It's undefined. Same thing happens here. Notice, now look, if you go backwards in this code, look for the definition of X. Have I found it yet? What do? I got to the very beginning of the function, and what did I never find?
The declaration of X.
A declaration of X. See, so that means this X is undeclared. Now it should have been written this way. And now, well, where's that X declared? Right there. That's the X. It's the X that matches the input. Okay, same with here. Okay, now why is underscore allowed here?
X is declared in the first line.
Yeah, X is declared up here. X is the input to the function. So that X, well, it's declared two places. It's the X of the case. Actually, it's the X of the case. So this is a local block. So this X is the X of the case, and that X is that X. So it's actually there's actually two X's in there. This X is that X, and this X is that X. Okay? Can I put an underscore? Let's see. Now, here, what X is this? Is it this X? Is that X from here? What do you think? What X is this?
The X after F1.
Right. Yeah, what's wrong? What's wrong with saying that X is this X? Why is that a wrong thing to say? See, this is why this is a programming languages class. You have to start thinking in terms of explaining things using the language of programming languages. Okay. This is a reference to a variable X. There must be a place where X has been declared. Otherwise, I don't have an X. What's wrong with saying that this X is that X? It's actually this X, because what's the difference between this X and that X?
The first one doesn't have a literal.
I don't know what you mean.
We didn't. The first X that we declared, well, the one in that one doesn't have a integer literal compared to.
None of them have an integer literal.
Oh yeah, no, that's comparison. Never mind.
Those are right. Those are not assignments. Those are comparisons. Yeah, those are comparisons. Okay, so what's wrong with saying that that X is that X? Because that's the first X I see. What's the difference between that X and that X? Remember, there must be a declaration of this X. Where does this X come from? Does it come from that line?
It comes from the first line, right?
Right, that's the declaration. I'm saying that my function takes in a parameter called X. That's the declaration. So this X is that X. This X is that X. This X is that X. And so is this one. This X is that X. These are uses of that declared variable. That's the declaration. These are all uses of it. Okay? that's the declaration. Now down here, there's no variable declared yet. I'm saying patterns. If F2 is given 0, you output 0. I'm not even saying that I'm not declaring any variable. I'm using a pattern. So I'm saying if F2 is given 0, you output 0. If it's given the integer 1, output 1. If it's given the integer 2, output 2. Then here I declare a variable. I say, oh, if it's given a value named x, which is not 0, 1, or 2, because 0, 1, or 2 have been matched here. So if it's given a value named x, I want it to string the x. So this x is that declaration. Okay, this x is kind of like, but not exactly the same thing as this x up here. Kind of, but not quite the same thing. Because this is an x for all the values here, all the values, whereas this is only used if you didn't get a 0, 1, or 2. This only comes into play if the input to the function wasn't 0, wasn't 1, or wasn't 2. Then it gets bound to x. Here, all the inputs get bound to x, and then you decide, well, was x 0? Was x 1? Was x 2? Otherwise here. So this is kind of a little bit different. All the inputs get bound to x, and then you figure out which x value it was. Here, 0 gives you 0, 1 gives you 1, 2 gives you 2. Any other value gets bound to x, and then I use the x here. Okay? Same here. The function takes in an input. If it's 0, give me out 0. If it's 1, give me out 1. If it's 2, give me out 2. So far, no variable's been declared. Then here I say, oh, if the input's anything but 0, 1, and 2, call it x. So I'm declaring the x. So this x is that. If I put a underscore there, I didn't give the input a name. So this x was never declared. This would match 5. If the input was 5, this would match 5, but I wouldn't have a name for 5. It would really be an anonymous number at that point. We were talking a little earlier about anonymous numbers. That's how you get an anonymous number in ML, by matching it with underscore. Okay, but then you can't use the anonymous number. It doesn't have a name. Here, this just says match anything that's not 0, 1, or 2. But what you're toStringing is the thing you're casing on. So you're saying is take the input and call it x. So it's kind of like this case up here. Take the input and call it x, and then check, is x got the value 0? Does x have the value 1? Does x have the value 2? But notice that 0, 1, 2 are values of x now. Does x have the value 0? Does x have the value 1? Does x have the value 2? Does x have any other value? Then print x. See? But that makes sense. If x has any other value, print the x, because the x is bound to that guy there. That's why this underscore makes sense and this underscore doesn't. Notice that this example is kind of nice. This little function here actually has a lot of information of how to think in it. So it's kind of a nice little, to me, I use it, I go back to it actually kind of often to remind myself of the syntax of all these things, because there's such little changes in the way these things work. Okay, little subtleties in the way they work. Okay, now this one used the fun notation like this one did. Now this one uses the FN notation like this one did, but now it's the FN notation with a case statement. Okay, this is the function. Now it's a function literal. Notice that this was not a function literal. This was a function definition. Here I'm doing a function literal. The input is x. So I've got an x. I've declared an x. That's the input. Then I case on that x. If x is 0, output 0. If it's 1, output 1. If it's 2, output 2. Notice that here I've got 2 x's. Here I only had 1. Well, here I have 2 x's, and here I also have 2 x's. Okay, here is the x that's the input to the named function, and then I case on that x. Here's the x is the name of the anonymous function, and then I case on that x. Okay, so this x is kind of almost exactly the same as that x, and this x is pretty much the same as that x. In a way, this is kind of funny notation, because if you're going to use the fun notation, the FN notation, why do you need the case? Why not just use this? You know, but if you look in the world of ML, some people like to define, some people like to use this, some people like to use this, some people like to use this, some people like to use this. Okay, here I'm using an anonymous function, and I'm notice that, so that means I only have to define the function one time. Yeah. Well, actually, even here, I only had to define the function one time. Actually, I think this is a notation a lot of people like, because it gives the function a name right away like this, but you don't have to repeat the names over and over again. So this one, I think, is actually the one that a lot of people prefer in style. You're defining the function only essentially one time, so the name only shows up once, and then you get this case with the rules, and that gives, you know, it. Trying to think of like why it would be why this. I remember I think this is the one that people kind of prefer over this. They prefer it over this because this one has the disadvantage of having to name the function over and over again. That's the complaint about this notation. You have to keep naming the function. Try to remember like why out of these two people prefer this one. I think because they just prefer the fun notation. You know, this one, val. There's two keywords kind of in there. Though here there's two keywords also. Here there's three keywords, val, fn, and case. I think this one does, I don't think people use this one all that often. So I think this is the one that is preferred by a lot of people. You know, I think they think of this one as the most kind of optimal design. You only define the function once, and you use these rules instead of clauses. The clauses have the disadvantage of needing the name over and over again. So the clauses have that slight disadvantage. Okay, so there's just more than one way to skin a cat here. Okay, you can define, now almost nobody does this. You should use pattern matching. You should not define functions without pattern matching. Unless you have a good reason, you shouldn't define functions using if, then, else's. Okay, so you should use either clauses or rules. Okay, and you use clauses in a fun definition, you use rules in an FN definition, and you use rules in a case definition. So you're way better off using clauses and rules, not this kind of thing. Use pattern matching, and then, you know, it kind of boils down to whether you want to write this, I think, or that. I think those are the two that people prefer the most. Though I can see people preferring this one too. This one I don't think people use that much because it's a val and a fun and a case. It just seems like overkill. I don't know if there's a good reason why you would want to have all that. Okay. Again, there's a reason for this because it got rid of all the repeated names, but so did this. So I'm not real sure. I think there are technical advantages to the case statement. In some cases, I think the case statement might be a little bit better than just these rules without the case statement. Okay, so I think that's why people prefer this one. I think the case statement is pretty versatile. So this one kind of is like a little bit of a convenient general way to program. Most books teach ML this way. That's the way it's usually taught. Probably that's the way most people program. But I've seen people say that this is better. Okay, so that's what the book means. Now, the book, when they talk about more pattern matching, that's what they mean. They meant pattern matching in the case expression. But what I actually show you is a little bit more. There's really this, the pattern matching in the case notation can also be used in these rules in the FN. So the book didn't kind of point that out. So the book just kind of jumped from this to this and didn't point out that there's these other two here. Okay. So, and actually they just did cases without even function definition. So the book, I thought they kind of obscured what they were trying to get at. Okay. So notice that, see, this is a function definition, then this is no longer a function definition. So I thought that's kind of confusing because he's going from defining a function to something that's not a function. See, it's just a case statement by itself. That's just a case expression. That's not a function. So then it gets kind of, I think he made it kind of confusing. Again, that's not a function. That's just a case expression by itself, which isn't very useful. See, here I use the case expression to define a function, which is really what you want. You want to use case to define a function. but he kind of just, I don't know, he starts with pattern matching in a function and then says, oh, instead of patterns, you can use cases. Instead of clauses, you can use cases, but he dropped functions and he just started doing case statements as standalone expressions, which is not useful. See, again, still a case statement is a standalone expression. And I think that really goofed things up. Then here, he's comparing a case to an if. Okay, well, that's up here. There's the if versus the case. But the point is to define a function, not to have an if statement by itself. Now, you can bury cases inside function definitions. So I think that's what he's getting at, that you could define a big function and in the middle of it have a case expression. So that's useful. But he didn't point out that it's also useful this way here as a way of defining functions, as opposed to a step in the middle of a complicated function. Instead of talking about a case somewhere buried in the middle of a function, he should have shown you how to use case to define functions, because that's what people do. Instead of defining their functions this way, people often define them exactly this way, using a case statement on the right-hand side of the function definition. And they do it to say, they basically do it because clauses require you to repeat the function name, cases don't require you to repeat the function name. So the function is just named one time here. Okay, so he never pointed that out. And I think that's what he should have pointed out, because that's actually a really useful thing to know about ML, is that people will replace this with this, or sometimes this. Okay, but as he is right in that the case statement by itself is useful when you're defining complicated functions. It's not unusual when you're defining a fairly large, more complicated function to have a case statement somewhere buried in the middle of it, as opposed to here where the case statement is the function body. But see, even in these simple functions, it can be useful to have a case statement be the body of the function. All right. So,
Question.
yeah.
Is there any significance to using either val or fun, like for F3 and F4?
No, they're literally equivalent to each other. Actually, ML translates, the first step the compiler does is it takes this guy and turns it into that guy. That's actually the first step of the compiler. Funs, like this fun here, the compiler turns it into that immediately. So the fun is just kind of a convenient notation. The compiler rewrites it using val right away. That doesn't mean you should write it using val. This is a pretty readable notation. This is a pretty readable notation, but the compiler actually recompiles this into this. The first step of the compiling step is to rewrite funs using val. Okay, so there is no difference from the point of view of ML. The only difference is in readability. You might think that this is more readable than this. Other than readability, there's no real difference. Okay. And like I say, the compiler, from the point of view, this is the lower level ML. So this is like a higher level piece of ML that gets translated into this slightly little lower level of ML. And then that's what the compiler compiles. It translates this to this and then compiles that one. And similarly, I think this one gets translated into this and then that one gets compiled. Okay. Right. So you pretty much can use any one of these. The only one I wouldn't recommend you ever use is this. You should use pattern matching. All of these use pattern matching. So the key is pattern matching is really important in ML. Functions should be written using pattern matching unless you have a really good reason to. Remember, we saw that the compiler will notice when your patterns aren't complete, but when you write if statements, the compiler won't notice if your if statements have a hole in them. If I drop that, the compiler won't say anything. If I drop that, the compiler will say you have a hole in your function. It'll notice it. It'll notice the hole in that function. It won't notice the hole in that function. That's a good reason to use patterns. The compiler is smarter about them. The compiler seems to understand them better, and it can detect when a pattern is incomplete, but it can't detect if statements are incomplete. And you can get very subtle errors that way. You can have subtle mistakes in your code where you're missing a case in your if-else statements. So the compiler is very good about checking your patterns to make sure that they're all there, that you didn't lose a pattern. So use patterns, don't use if statements in ML. But then but all these use patterns. So from the point of view of ML, doesn't really matter which one of those four you choose. It's more readability. Okay. All right. All right. So that's the next step in this chapter. Okay. Now that brings up the real heart of the chapter, the higher order functions. Okay. Okay. So what's a higher order function? If you Google higher order function, you'll get just a huge amount of stuff. And in fact, what's interesting is if you Google higher order function right now, almost everything you get will be about JavaScript. You notice I just Googled higher order functions. JavaScript, JavaScript, well, Wikipedia page, JavaScript, JavaScript. Okay, a language called Clojure, Scala, Lisp, okay, JavaScript. Yeah. This one's this one's ML. This one down here is an ML. This is a book on ML that's actually kind of nice. Okay, well, actually, but it's not about the dialect. I would use this book for our class, except it's about a different dialect of ML. So it's not usable for this class. It's a dialect of ML called OCaml, OCML. It uses this dialect of ML, but it's a very nice book. Okay, I think the book is really, really, really well done, but the language is all a little bit different. Like you use let instead of there, and there's several other things that makes it, you have to translate between the two languages. So OCaml is a dialect of ML. Okay, but notice that JavaScript makes lots of use of higher order functions. So higher order functions, and Java does too at this point, but right now, the people who are really interested in higher order functions are the JavaScript people. You know, if you kind of go through this, you'll see that the great majority of the hits on higher order function are going to be about JavaScript. Okay. So every JavaScript book now has a chapter on higher order functions. Okay. So what are they? Okay. Higher order functions are, let me see if I have let's see. Let me just, okay. Whoops. It's kind of a funny phrase, higher order. It comes out of logic. It's a term of art. Higher order is a term of art that logicians use. It means a function that takes in a function. I'm sorry. Excuse me. A function where one of its parameters is a function, or a function that returns a function. That's a higher order function. Its input is either a function or returns a function. For now, let's worry about the input case. Okay, so let me show you some simple examples. I'll just write them in text. Here's a function that takes in a number. I'll think of that as a number and another function. And what does the function do? It computes that function on the input number. There's an example. There's like a famous simple example of a higher order function. You give it a number and a function, and it plugs the number into the function. That's what it returns. So the function's input is a function. Okay, I can do that in ML. Here's how I'd write that in ML. I would say fun f of x h equals h of x. Okay, or if I want, I can write it h of x, but I don't have to write it that way. I just say h of, the better way to say is h of x. Okay. Now what did it do? Notice the type signature. I defined a function that takes in a thing of type A, and it takes in a function from A's to B's, and it gives me back a B. See, so what it did is it took that, it's a function. What it's going to do is it's going to take that input, plug it into that function, and get back out a B. So f is a function from, say, number to something, and it gives me back a something. Now here, let me use it now. Okay. I'm going to apply f to the function, to the number 5, and now I'm going to give it a function. And what I'm going to give it is an anonymous function. So here's where the anonymous functions come in. I'll say my function h is fn x goes to x squared. Okay, now I need to group that in parentheses because it's a bunch of p's. So I'm going to say apply f with the number 5 and the squaring function. Okay, if you square the square, whoops, I'm goofing up. You get back 25. Okay, 5 went into x. This function went into h. Then I computed the function of 5. The squaring function of 5 is 25. If I apply that function to 7, I'll get 49. Here's the cubing function. Okay, so I'm going to apply the cubing function to x. Okay, I get back 343. So I've got a simple little higher order function. My function f takes in a function h, and here, this is where anonymous functions become real useful. Anonymous functions are quite often the inputs to higher order functions. That's actually a very common thing to do. So if I over here, I'd be saying that f of 5, I use a more Java-like notation, x goes to x squared. Okay, so call f with the value 5 for x and the value x goes to x squared for h. See, that's why we call this a function literal. That literal gets plugged into there. This literal gets plugged into there. You can call this an anonymous function, but you don't call this an anonymous number. You call it a number literal. And that literal value gets plugged into that variable. This function value, this function literal, gets plugged into there. So then the right-hand side becomes squaring of 5, which is 25. So this will give me the answer 25. Okay. What it really does is it takes the function x goes to x squared and gives it 25 as its input. So it really takes, if I think of it evaluating in steps, 5 went into the x goes to x squared went into h. So I have h of x, which is going to give me 25 times 25, okay, which then gives me, well, I don't know, what's 25 plus 25? Oh, I'm sorry. It was 5 here, and then that's 20, then 5 times 5 is 25. I was talking and not thinking. Okay, there. Okay, so f of 5, x goes to x squared. The x goes to x squared is the h. The 5 is the x. So I have h of x, and h of x takes the 5 then as the next step and plugs it into there. So I get 5 times 5 is 25. Notice that I'm evaluating a function in fast evaluating a function. I pass that parameter to there. I pass that parameter to there, which gives me this. Then I have to pass that parameter to there. And I get this. And then I get this. So higher order functions involve higher order. See, there's a higher order of thinking because there's a two-step process involved here. You're passing a function to a function, then usually you'll somehow evaluate the function that's the parameter. So that means that in the process of evaluating this function, I end up doing more function evaluation. So I pass these parameters into there. That gives me this, that gives me this, and then, of course, that parameter's got to be passed into there. So I've got a function call inside of a function call, okay? So that's a real simple example of a higher order function, okay? And then I could, here's another example. I can have a function f that takes in two functions, g and h, and gives me, and then a number x, okay? And the function will give me out, I'll do what's called composition. I'll take g of h of x. Okay, so there's a higher order function that takes in two functions and a number or a value, because in ML, this is going to be, this could, over here, notice that f didn't say that it had to be numbers. Let me do f a little bit fancier thing. Okay, so f of a string, cat, and my anonymous function will be fn takes in something, which I think it was a string, and it gives me out the string concatenated with itself. So it's like a doubling function. So there's a doubling of string function. Okay, so there, now notice my anonymous function says, give me a value and give me a function, and I'll apply that function to the value. And see, it's a polymorphic function. So the value can be any type as long as the function takes in that type of value. Then it'll plug that value into the function to get something out. Okay, so here what I'm going to do is my function takes in a s and gives me out s concatenated with s. So that means that s is a string. Okay, and I need to, I got the grouping wrong. So call f with, I was thinking I was writing Java there, but I'm writing ML. So here's how I'll write it. F takes in cat, and the function that takes in a string and concatenates the string with itself. It's a polymorphic thing. See, I get out cat, cat. My higher order function is very polymorphic in this case. I have a very polymorphic function. It just says, you give me an input and an appropriate function, and I'll apply the function to the input. Here it was, the input was an int, and the function was from int to int. Here the input was a string, and the function was from string to string. Here's another example. I'll do f of the number 5, but the function will take in a number, and it'll give me out the real value of that number. Well, will give me 1.0 plus x. Okay, so that's going to increment the number. Now, let me, yeah. So x is going to be an integer. That integer is going to be converted to a real number, and then I'm going to add 1.0 to it. So I should get out 6.0 from this, because my function takes in my function here takes in an int and returns a real. This is an int. My polymorphic function takes in a type A and a function of that type. Well, this is an int, and this is a function of ints. So this will work. See, I get out 6.0. If I tried the following, I'm going to get an error message, because that's a real, but that's a function that takes in an int. It will not promote, or it won't do any conversion for me. So this is going to give me an error message that if you read it real carefully, it's going to be saying, this guy expected an int, but this was a real. Okay, so F failed because it didn't match this type. The type of A here didn't match the type of A here. You had a real here and a function from int to real here. So there was a type mismatch. Okay, but my higher order function is very polymorphic. Yeah, you can see it here. It's got lots of type letters in it. Okay, now let me do this one. This is going to be even more polymorphic. I can do this one. So this is a function that takes in two function parameters and a value, plugs in the value into one of them and gets out an output, and then plugs that into the next function. Okay, so that's called composing. It's g of h of x. So over here, that would look like the following. F, okay, fun f, I'm going to change f is, of g, h, and x. Fun of g, h, and x will be equal to G of H of X. Okay, that's how I would write it in ML. I don't, this is the math notation, the Java notation, but ML's notation is a little bit different. This says plug, actually, I'm not even, yeah, I do need the parentheses. This says plug X into H, and then the output of that gets plugged into G. Okay. Okay. So there's my function. Now it's very polymorphic. It takes in a function from A to B, okay, another function from C to A. It takes in a C and gives me out a B. So the C is the X. Then the G function is the function that goes from C to A's. So the A is the output of H. The A's are what goes into G, and the G gives me out B's. Notice it didn't put them in a nice order. You kind of thought it would be like from A to B, B to C, and then this would be A to C. So, but because of the way ML works, it analyzed this thing in its own little way of thinking, and it gave them the type letters have kind of a funny order. X is the number, that is type C. X is the input to H, because we see that here. So H is C to type A. Okay. Then the output of H goes into G. So type A has to go into G, and G gives me out some type B. Okay. And a real simple example of that would be, say, I'm going to apply F with, okay, I'll make G the squaring function. I'll keep it simple. G is the squaring function. H is the cubing function. I'll make H the 2 times function. Make it even. So H is the function that just doubles a number. Okay. Okay. So I have the squaring function and the doubling function, and I'll give the number, say, 3. What did I do wrong here?
You have to put the FN in between or before the X's.
Oh yeah, I forgot the FNs, because in some languages you don't need the FNs, and here this to say that these are function literals, I have to say function literal. So I have to say the FN notation. Yeah, like in a lot of languages you don't need that little extra thing. The arrow is enough to say it's a function literal. So in a lot of languages the arrow alone denotes it as a function literal. Okay, so I forgot the FNs. Okay, so what did I do? I took 3. Let's see. Why did I get back out 25? Oh, 3 went into 2 plus 3, which is 5. Then 5 got squared to 25. So the 3 went into G. Well, the 3 went into the H, and then the output of the H went into G. So it went this number went into H, then that output went into G. So 3 went into 2 plus X, gave me 5. 5 went into squaring, gave me out 25. Okay. But it's a very polymorphic function. I could apply that function to all kinds of funny functions. I could make any, this will work with anything as long as I get those types right. This will work with any kind of function as long as I have to line up all the little types there. The input number has to be the input to the H function, and I have to make sure the output of the H function has to go into the G. So let's try to do something a little bit more complicated. F of let's make the input the string cat. Okay, so what can we do first with a cat, with a string? We could take the string and, well, before we made this, we concatenate the string to itself. Okay, so that would be S. Okay, so that gives me a new string. Now, what's the function that takes a string and computes its length? So Fn of S goes to, does anybody remember what the function is that computes the length of a string in ML? Does anybody remember it? Let's see if I can Google it real quick. See if I can Google the function that. if you Google ML, you get machine learning. So I realized the thing to Google is SML, because that's the version of ML we're using, standard ML. And SML doesn't get confused with machine learning. If you Google ML, you'll just get everything about machine learning. So, oh, size. Okay, let's see. So let's see if this works. String dot size. Okay, so now my function takes in a string, a function that doubles the length of the string, and then computes its size. So let's see if this one works. Okay, notice that it auto-loaded the string library. Oh, I didn't get the right answer. Let me try it again. I got back a function. The answer was function. What did I do? See, what did I do wrong? I got back that the answer is a function from string to int. I thought I was going to evaluate the function. Did I goof up the parentheses or something? Oh, I forgot to say. Yes, I forgot. I forgot the s here. I want the string dot size of s. See, this function takes in an s. That's the input to that function. And I want to compute the size of s. So since I didn't evaluate the function, it was returning the function itself. So that was my mistake. I wasn't evaluating the function. Okay, so now it should be okay. There, 6. Okay, and if I give it cats, it's going to give me back 8. Okay, now the function, the polymorphism was input was a string, this converted string to string, and this one took string to int. So the result was string to int. But my function f is very, very polymorphic. It's a higher order function, but it's a higher order function that can take in any function g and h as long as they match up in the appropriate way. As long as the output of h goes into the input of g, they match up. Okay, so I have a very polymorphic higher order function. Okay, so what we'll do is we're going to quit now, and on Thursday we'll just keep seeing why this is useful. Like so far it's just a little trick. Okay, I can write a function that takes a function as an input. Yeah, I haven't done an example where I have a function that returns a function as a value. That's a little bit less useful for now, but we'll see in next time. This is tremendously useful. This is a hugely important pattern in modern programming. And we'll see that Google makes billions of dollars on this pattern. The servers in Google are essentially doing higher order functions. That Google based their company on something called MapReduce. Yeah, Google the company is actually essentially based on something called MapReduce, which is a higher order function. Okay, so if you look up MapReduce, you'll see that that's the key data processing model invented by Google, and it's a form of higher order function that it's the idea behind how all their servers work. Okay, so we'll see what map means, and we'll see what reduce mean. Those are higher order functions, and then they're often combined together in what's called MapReduce. Okay, so map and reduce are going to be the higher order functions. In the point of view of the textbook, that is what they meant here by predefined higher order functions, map and reduce. That's what he's going to do. The two predefined higher order functions are map and reduce. Okay, so we'll quit there. We'll do a little bit more explaining of what higher order functions are, and then we'll see what people do with them that's so useful. Why the JavaScript people are so into higher order functions now. Like when I Google higher order function, you just see JavaScript after JavaScript after JavaScript explanation of higher order functions, because it's got a lot to do with this map reduce idea. That's a key idea. That's one of the key ideas that makes this higher order functions so important. Okay, so we run out of time. So remember, you have a homework assignment due. If you have questions about it, you can come to office hours or send me an email. And there'll be a program assignment that involves some of this higher order function stuff up in a couple days. Okay, and anybody get last second question? Any last minute question? No. Okay, so I'll stop sharing. Meet again on Thursday. Bye.